In the next part of the course, we're going to be looking at the physical properties of organic compounds and what influences particular physical properties, such as the melting and boiling point and the solubility in water. There's a couple of key components of the structure that you need to be able to recognise when doing this, and then acknowledge the significance of these in different situations. So one of those components is the non-polar hydrocarbon component of an organic molecule. So we can see here, this is when we've got our carbons and our hydrogens here. So this is our hydrocarbon component. It consists of the carbons and hydrogens, and it's the non-polar component of the structure. In this case here, we've got a non-polar component along there. You'll notice in this case here, we don't really have a hydrocarbon chain, so a fairly insignificant non-polar proportion of that molecule. The other feature which is important to recognise is the functional group, and quite often functional groups in organic compounds are polar and therefore capable of different types of secondary interactions than the non-polar hydrocarbon chain. So in this case here, we've got a hydroxyl. In this case here, we've got a carbonyl. And in this situation here, we've got a carboxyl group. So recognising the non-polar and polar components is really important in terms of then recognising the strength and types of secondary interactions. So the two key things that you need to be able to explain in terms of organic compounds are the trends in melting and boiling points and also the solubility in water. So you need to be able to decide or explain if a particular compound would be soluble in water or why one might be more soluble than the other, and also explain why one substance might have a higher boiling point than another. So firstly, we're going to have a look at melting and boiling points. And the melting and boiling points of substances is all related to the strength of the secondary interactions that are going on within that substance. So the interactions between one molecule of the substance and another molecule of the substance. And the stronger those interactions are between the molecules, the higher the melting or boiling point is going to be. And the reason for that is because it takes more energy to overcome them. So basically, if the molecules are held together more strongly, so when I say held together, I mean one molecule being attracted to another molecule strongly, it's going to take more energy to overcome that interaction between the molecules, and more energy relates to a higher melting or boiling point. Now, in terms of the strengths of secondary interactions, there are a couple things to consider. So the strength of secondary interactions is going to be influenced by two key aspects. So the first of these is the size of the molecule. And in organic compounds, what we're looking at when we're talking about the size of the molecule is generally the carbon chain and the length of it. The larger the non-polar hydrocarbon chain, the larger the molar mass is going to be. And we know that the molar mass is related to dispersion forces. So the larger the molecule, the larger the hydrocarbon chain, the stronger the dispersion forces are going to be. The other thing that's going to influence the strength of the secondary interactions is the presence of polar functional groups. Because polar functional groups are going to introduce different types of secondary interactions, such as dipole-dipole interactions or hydrogen bondings, and therefore possibly increase the strength of secondary interactions as well. So in terms of this, you need to acknowledge that the stronger the secondary interactions, the higher the melting or boiling point, and that the strength of secondary interactions is influenced by the size of the molecule. The larger the molecule, the stronger the dispersion forces, and also the ability for dipole-dipole interactions or hydrogen bonding, which is related to the polarity of the functional groups. The other thing you're going to need to be able to do is explain the solubility. So solubility in water of organic compounds. So that's whether they are not soluble in water, or whether they have good solubility or high solubility in water. And what makes an organic compound soluble in water is its ability to hydrogen bond with the polar water molecules. So basically, the greater the opportunity to hydrogen bond with water, the greater the solubility in water. So what this means is completely non-polar molecules are not able to hydrogen bond with water, so they won't be soluble. Whereas anything which has a amine or a hydroxyl or a carboxyl, which can hydrogen bond with water, could possibly be soluble in water. Now, what you need to consider is the relative influence of that functional group in relation to the non-polar component of the molecule, and also the number of sites where hydrogen bonding is possible. So the more functional groups, so for example, if it's got 2 or 3 hydroxyl groups, will increase its solubility. So in a situation such as this, where we've got ethanol, we can see that we've got our hydrocarbon component over here, so this is non-polar, but then we have got our hydroxyl group here, which is quite polar and capable of hydrogen bonding. So what we actually get occurring is our hydrogen bond between the strong partially positive charge on the hydrogen in water molecule and the partially negatively charged oxygen in that hydroxyl group. So the more opportunities there is for this to occur with a particular molecule and water molecule, and the smaller the non-polar hydrocarbon chain, the greater the solubility is going to be. So for example, if we were to compare a series of primary alcohols, each with one hydroxyl group, what we notice is that in each case, the non-polar hydrocarbon chain is getting longer. So they've all got one site for hydrogen bonding to occur with water molecules. However, as the chain gets longer, the significance of this non-polar component gets stronger, and therefore solubility decreases. So the methanol would be more soluble in water, for example, than octanol, which may be considered insoluble in water because although it does have this one site capable of hydrogen bonding with water, it's got a much more significant non-polar component, so it would be considered non-polar overall. So just to recap, you need to acknowledge that the boiling point of different organic molecules or substances is related to the secondary interactions that exist between the molecules. So the stronger the secondary interactions, the stronger or the higher the melting or boiling point. And you can determine whether or how strong those secondary interactions might be based on both the size of the molecule and the polarity of the functional groups. The other thing that you're going to need to be able to discuss and explain is the solubility of particular compounds in water. So basically, the greater the opportunity to hydrogen bond, the greater the solubility. So again, you're going to be considering the non-polar component of the molecule in relation to the polar functional groups which are capable of hydrogen bonding.